So today we're going to talk about some Scrappy set snooping. I've also given this talk with some other people under the term Project Mid-Haul. I'll explain that's kind of like a little side joke about what that is. We'll talk about that when we talk a little bit about satellites and satellite communications. First, we'll start with a little bit about myself. Name's Cody. I'm a senior engineer at Praetorian on our IoT pod, doing security assessments on hardware and other IoT devices. I spent 13 years-ish in the Army, doing a lot of different stuff. I spent my last good chunk of my tenure there at U.S. Army Space and Missile Defense Command and Tactical Ground Operations. I'm a big RF SDR enthusiast, so if you like RF stuff or have anything that's really cool, let me know, because even if I can't legally touch it, I'd love to see it. Um, I'm obsessed with drones, rockets, and satellites. I do some DIY drone building. I will hopefully be getting my level 1 rocketry cert soon. And as you'll see in this talk, I like to tinker with some different satellite stuff, stemming a little bit from my experience getting to work with all sorts of satellite payloads in the Army. Prior to doing security, I spent about a decade working as an audio video engineer, designing audio video distribution products. So also HDMI, all that kind of stuff. If you need any questions about any type of video standards or EDA decoding, you can reach out. I can help you out. In general, I'm a serial hobby collector. So sewing, metallurgy, woodworking, pretty much anything that involves creating or crafting something. I probably have too many tools in my garage that my wife wants me to get rid of. Also, I'm looking for like really good suggestions on cheap fiber lasers right now, in case anyone knows. So let's talk a brief moment about satellites. What makes a satellite both fun and hard to listen to or talk to? There's a couple different orbits of satellites. Definition of a satellite is technically any body that's revolving around another body in space. And in our case, we're going to be talking specifically about electrical or communication satellites that are revolving around Earth. There's a couple different like orbital like distances. You have LEO, MEO, GEO. I'm not going to get in those, but one thing I want to talk about is the geostationary orbit, which is pretty far away, and we're going to talk about some polar orbiting satellites today and what we see with those. As those satellites are out there flying around the space, they have what we call a footprint. So if you hear that term, that's the area on the ground. There's kind of two connotations, an uplink footprint and a downlink footprint. An uplink footprint is where you can be on the ground looking at the satellite and successfully transmit to it. The downlink footprint is where you can be on the ground and successfully receive from. Just because you can see a satellite or you have line of sight doesn't mean that you can talk to it. It has to do a lot with antenna polar patterns. Older satellites are a lot more forgiving, where you generally just have a big circle or a big ellipse. Modern satellites have regenerative transponders, and what those can do is a combination of beamforming and antenna array rejection to selectively pick locations where they can and cannot receive or transmit from. So their accuracy isn't like to like one house or one building, but they can block out and say, hey, I'm going to transmit only to one city and nobody else can see it. So this is what a satellite might look like in space. There's going to be a lot of different like sensors, payloads. The ones that we're most interested in is anything that's doing cool, fun things and then sending that data back down because we want to listen to that. The most common one, which is the same thing that we did in these projects, is going to be looking at like NOAA and WeatherSats. All of these satellites are actually managed by what was the Air Force, now the Space Force, in terms of like orbital flight path, maintenance, things like that. So when you talk about like the NOAA satellites, they belong to NOAA on budget, and they are like the primary users of the data, but it's all managed by Space Force now. They have a couple different types of satellites for NOAA, and you'll see ones with NOAA designation. Those belong in their low Earth orbit, so they're not that far up, and they go around the Earth in a polar pattern, and they're doing some pretty quick stuff. They're not really great in terms of like picture quality or like other data. Most of those are legacy systems now, and they just haven't, fallen off the planet. So if you look this up, you can say, hey, DIY sat receiver NOAA, there's tons of other material that'll cover the same thing we're going to talk about today. NOAA, after a lot of people started figuring out how to do this, and NOAA realized a lot of people wanted to do this, and a lot of the amateur radio people were interested, they released a guide on how you can accomplish the same thing. And you can do it with pretty much just those three components. If you're very lucky, the quality is going to be very poor, but we're going to do that actually today. And basically, you can just turn that into a satellite dish receiver. So these are a handful of different protocols that the weather satellites use. The ones that we're looking for at the LEOsats is going to use APT. We're looking at 130 megahertz, and these are reduced resolution images. They're very low quality. The orientation might be wrong. There's no additional data that's coming along with that. So when you grab that specific feed, you're only getting basically a poor quality camera feed, and it's all line scan. You're not getting like a whole picture at a time. You need to continuously read, and you'll get like a little strip of the tiny bit of land that can see it at one time. I'm not going to dive too deep in the protocol. I just wanted to show essentially over time, you will receive that data in series, starting at the top left to the right. And once it finishes the first line, it will just start transmitting the second line. So if you miss them, they're just gone. There's not really much error checking. So when you try to decode it, if you have errors or stuff, you're just going to see static or wrong information. And then there's some sync frames to help software identify where that is. So where do these sit? These NOAA-SATs are about 500 miles from sea level up above Earth, and they are orbiting pretty quickly. Individual passes depend on where they are in the sky. So if they're going dead overhead, you probably can get, it's been a long time since I looked at the numbers for this. I want to say probably like an 11-minute pass. Most of the time it's going to be a little bit less. I think like on average, you're looking at like 6 to 7 minutes from when it comes up over the horizon on one side and down on the horizon on the other side. So at the time, this was taken, all of these pictures that you're going to see in this presentation, and this project was done at the beginning of 2020. I was out helping take and teach classes for the Army in Pennsylvania, dealing with satellite communications, and they were paying us a pretty good stipend for our food allowance. And so if you just search per diem, Google will correct you immediately and tell you that that's actually extra antenna money. So you can go on Amazon and buy a bunch of cheap stuff. Most of this we ended up not using or didn't need. All of the stuff here is going to cover two different projects that we did. But really, the primary components that we're going to use for the first one is going to be the RTL SDR dongle that's up there. And actually, the wire I don't even think's on here. We bought the wire that we used from Lowe's. So we went and got just home a wire that run 14.3 through your wall, stripped out the wire, and we use that as our conductor. See a couple of the people I helped. You'll see this gentleman on the left, a friend of mine, Alexander Bolia. We do a lot of projects like this all the time, and we were helping teach the other people here all about different like basic antenna theory, like dipole antennas, quad helix, stuff like that. And so here we were showing them how to solder two wires together to make the worst antenna you'll ever see in your life. This is our PVC mounted dipole antenna. We ran a coax cable through the PVC and electrical taped everything together. And we were able to go out and use that along with a app on our phone to track where the NOAA-SATs were. We were outside waiting, and we were able to see on the RF spectrum, and we tuned in, we were able to see some data, which was great. But we only got very, very short readings, and we couldn't actually decode these, not successfully for something viewable. This kind of can be hard to see here. If you look, this line appears to shift in comparison to the rest. One thing that I want to point out is Doppler shift. So especially with LEOsats that are moving very quickly, your antenna tracking system and your decoding system needs to handle their speed and the shift of the frequencies due to their movement. So as they're moving, you'll see on the spectrum, their data lines will shift as they approach or depart overhead, depending on the distance from you. We upgraded a little bit from having to like stand in one place, and we were mostly focused on trying to just get one good read, even if it was just for like literally a couple seconds. And we got really tired of standing out in the cold. So we upgraded our antenna by taking apart two broomsticks and taping them to this to create like a makeshift tripod. And with that, let's play here. We were able to get a relatively good read. So this is what that looks like when you're receiving it. I love watching this. It's just, even before you decode it, it's really cool to show people. The first time that you get to go out with a handmade antenna and see this, it is just an absolutely great feeling. So I love just getting to see that. We eventually decided to experiment. We tried a couple other different things. We got some like solid aluminum and some solid copper pipes, or sorry, not solid copper, but copper pipes. And we tried various configurations. We got smarter and made a little H brace on the bottom for our PVC mounts. Um, Ironically, the really bad wire dipole we made was way better than any of the other ones we made. And we never quite figured out why, because the length of the conductors were the same. I think it just had to do with the like coupling of how we had mounted these, because we didn't solder to these. We used, sorry?
Solid wire.
Well, we had solid copper core wire for the first one, and then the other one we had used a solid, completely solid conductor, and then a pipe. So not sure. I think it had to do with coupling. There was a little block that we mounted these pipes to. I'm assuming that it was that, but can never confirm at the time. I did not have a spectrum analyzer. Um, so this was a really bad reading, and this is not a useful image. All of the stuff that you see here, all the nodes and all the color, is falsely applied by the software. So you can decode this once you have a good read with software called OpenWX that'll help you decode AVT signals. And you can apply it if it has just enough information. It will take and overlay um, some color and some like state country lines and coastlines. However, if you were to remove this, like this is mostly just static like this. You can see very little detail. Um, the only thing we were able to like accurately see was the markers on the start and end of the frames. But inside this image, without the false image, it actually doesn't have anything, which can be kind of misleading if it's starting to draw this on your screen. You're like, yes, we got this cool read, and then like you save and look at your image files after, try to decode it without this to just see the land, and you're like, oh, it literally just looks like white snow. So we built a third antenna. Uh, because we wanted to get a better read. Now this antenna is a lot more directional. So this was a quad helical antenna where we took multiple conductors and you wind them you make them a certain length and wind them at a specific rate. It's a lot more directional. And so we had to be pointing a little more precisely. It was a lot harder to get a good read. We probably spent like a week or two now spending, wake up at 5 in the morning, get done with Army at 7 at night, and then we'd probably be up to like midnight trying to get good reads and waiting. Between passes, you have to sit and wait.
When you say pointing more precisely, how were you even figuring that out?
Uh, a lot of trial by error. Um, so with a lot of phone apps you have, you can confirm that like your magnetic zero for your phone magnetometer is good, and then with your current location, it can determine where the satellite's supposed to come up and where it's going to be. So a lot of those you can see like here's the horizon, and you can see the satellite as it's on the other side of the Earth on your phone screen and where it's going to come up, and so you can see that orbital path. And so you wait and you hold your phone with the antenna like this, and you try to hold them together and then try to follow them. In this picture, uh, I had some reads when we were at this point. I believe inside the antenna, we had put a little like orientation sensor, and we had one of the guys who was probably somewhere behind the guy who took the picture reading out like how the orientation of the thing. Someone else was comparing that with the phone and telling me how to move it, which is not an effective way. We spent a long time only to get one good image. This was the one good image that we could actually identify something on. So as you can see, it's pretty much all white except for that blue. Does anyone know where this is? No. Does that help?
That's like Long Island, Boston.
Yeah. So why is this picture upside down? When the satellites are coming in a polar orbit, they're not always going to come up in the same spot. And so their time around Earth, the Earth will be spinning. So if the satellite's doing this and the Earth is spinning every time it comes around, it'll be going over a different point of Earth. And what'll happen is as you go on one pass, it might be going from north to south. And as Earth spins, next time it comes, it might be coming up from the south and going over the north. They don't orient that in the data they transmit. They're just looking at the image, taking that scan line data, and sending that down. So on some passes, your image looks upside down, and that's only because the orientation of the satellite and where it started from and where it's going next. Okay, so we struggled for probably like 3 weeks to get like one picture. So we figured if we wanted to start here, why not make it harder and go out here? Oh, kind of cuts off a little bit. Yeah, there is actually a dot over here. So, we wanted to go from the LEO sats for NOAA and hit something a little further out because that was hard enough. And so we wanted to hit GOES. And GOES is one of the satellites that lives in the geostationary orbit. And out there, you have kind of two two main areas. You have obviously where all like live satellites are, then you have a separate graveyard orbit. The benefit of going that far out, and specifically 22,000 miles out, is that it's the right speed, or it's the right distance and gravity's just right for them to use as little fuel as possible in order to match the timing of the orbit of the satellite with the rotation of the Earth. So you can look at a given point in the sky from a given location and know within a small degree of error that the satellite is in that location. So does anyone here have DirecTV? Obviously, I think most people know what DirecTV is, or like Dish Network. They are all in the geostationary orbit because if they weren't, your antenna that they put on everyone's house would have to be tracking. They would have to follow the sat as it moved, and they wouldn't have 24/7 coverage. They would have to have a much larger constellation that's constantly moving. Think like Starlink or even like GPS, where you're hitting a few different of the satellites at a time, and you would run into issues where, let's say, in the city, you might not have good connection in given specific locations. Uh, this is where we get to the long haul, and it's kind of the whole joke of the front of the slide. Um, in the Army, we refer to like a lot of our comms like ground stations. So if you're on site somewhere and there's commercial ISP and you actually just have like an actual internet line and they can encrypt and send data back, we call that a backhaul. I know like actual ISP and some telecom providers use backhaul for a different term, but the Army uses it like that because they like to misuse information. Um, and then we call the satellite over the horizon connections our long haul connections. So that's kind of where the joke comes from. This is a rough image of GOES. The problem is we very quickly realized A, our antenna is tuned for the wrong frequency, and B, there's no way in hell we were going to be able to just hold that thing and point it in the right direction. So we decided we needed a bigger boat. So we went searching around, and luckily for us, other people had already solved this problem, specifically not being what is the best antenna for the job, but what is the cheapest antenna that can do the job. And we found that there was a 1.9 1.9 gigahertz tuned antenna. When I don't have a section that shows the frequency here, but the protocols that they use for this aren't 1.9 gigahertz antenna. So if you were to use this as is, you may receive some very, very, very low quality signal, but it won't be usable. And so people online figured out that if you take this shield off, this is in the orientation we used it in, it comes in a different orientation. So if you take it off, disassemble it, add a couple more parts, and put that front part back on, what ends up happening is that the tune frequency that the antenna is designed for ends up never hitting that antenna, and the frequency we are aiming for comes in a lot better. There's a lot of math and science there. If you ever find the actual write-up that the guy did on a blog post, it's really cool. So that, yeah, this wasn't cutting it for sure. So we did this. And the problem with this is that it was not working. And we thought we just wasted $120 on an antenna for it to not work. I think I just checked today. It's like $175 for this antenna. And I'm not sure on like shipping availability. Why didn't it work and what struggles did we have? So at 22,236 miles from the Earth, it's a very small target to hit that satellite. With LEO, you could kind of like wave the antenna around and like happen to see it and like watch the screen and kind of just move it, once you kind of got on the satellite, you could kind of just move in like incremental circles and follow it through the sky if you know the rough path. And it was pretty lenient. If you were within a couple degrees, you're probably going to receive the signal, especially with the antennas we were using. The antenna we have is very, very directional. And out at that distance, 1 degree of error means that you're 288 miles off of target, and you will not even get an inkling of signal. So with these satellites, for the most case, at this distance, you're either going to have signal or you're not. There's usually not, I have like half the signal. If you have degraded signal, usually it's because of weather effects or polarization issues, but you're looking at the right spot. So we spend all of our class time, instead of taking the class we were taking, cutting up cardboard and trying to create prototype mock-ups of a ground station that we could build. Took that, threw it into some CAD software, rendered it, again, trying to be as cheap as possible. We designed the entire thing to be made out of plywood and bolts that were available from the Lowe's. Bought some power tools on Craigslist. I don't know if anyone's here was in the military, but you are not allowed to use woodworking power tools in a barracks building. That did not stop us. Um, that's one of the desks from someone's bedroom. They didn't have that to work with for a little while. We had a small jigsaw, the hacksaw to cut the bolts, and the belt sander. At this point, our instructors found out what was going on, and they were equally degenerate, so they didn't tell anyone, and they helped us get more tools. Um, Once everything was assembled, I did wire up for some servo motors. Anyone who did 3D printing before they got good might recognize this as a ramps board. I used this with an Arduino and programmed some firmware to control the servo motors so we could start kind of controlling where this thing was going to be rotating and looking at. It used some timing belts. If you ever do this, one problem you would have is the fact that timing belts, even though they're like kind of grippy and would work for like, I don't know, an actual gear, it tends to slip on plywood. So making plywood parts is not a recommendation that I would make for making geared movement systems. We solved some of that problem by flipping some of our belts inside out and stapling them into the plywood to give them a little bit of a physical grip on the bump, but as well a little bit of a different material to grip onto. Some of the parts were literally just hot glued down. Um, I believe we had to fix that after we broke some things. And you'll see this weight here on the right. This weight was designed to be adjustable, and the goal for that is to offset the weight from the antenna on the front, so that way it wasn't constantly pulling and having like put a lot of force on that motor. So even though the antenna is relatively light, being so far out on the arm would mean that you had a ton of force. So we ended up having to use a larger weight than expected. But we were able to adjust it, get it in place, balance it out. So by the time we plugged in power on the motor, it wasn't going to consume too much power and burn. Let's see here. So this is the completed unit, the antenna, everything ready to go. We had a PVC base screwed into the bottom, so we could just drop it onto a tripod that we borrowed from one of our instructors. He was really useful in providing these things. So it was a little weird when we went to the schoolhouse and walked out with a bunch of bags with his tools and tripod, but nobody questioned it. So just like a 3D printer, what we had was a homing motor, or a motor to move it, and then a a switch. So when it homed and hit that switch, we know that was 0, and that's where we planted that after we lined up all the parts, so we could tell it where magnetic north was. So this was our very first test run of this doing homing successfully, I should say, homing. So this was a big accomplishment for us and our firmware getting everything going. Later on, we added some compass and magnetometer information, so we didn't have to do as much setup, and we removed that switch and had some other mechanisms for performing that task. We would have to manually zero this to north, so we had a flat part on the back, and we would use a alignment compass, really cool compass that gets light from the sun on the top and has a dial, and on the dial that spins on the outside ring, there's all the measurement markers, so you look through it and you can turn and see where you're at. So we would line it up to north and let us do its thing. So now we got this thing out here. how do we know where to point it at? How do we control it? Everything like that, right? So you build all this stuff, you finally escape from the fish tank. Now what? So for us, what we need to do is track the satellites. And this, we built that specifically to hit GOES because it's so far away. But the same setup, we can replace the antenna and use it to track like LEOsats, like the first weather sats we did, and potentially other satellites. There's a handful of other interesting ones out there, and weather sats from other countries like China and Russia you can also listen in on. N2EO is a pretty good one for tracking satellites. It has a cool API. I don't know if they currently charge for it. That's kind of been an on and off thing with them. But it's the best API that I used. It shows satellites' current position. You can get a ton of information about the satellites. Some of this doesn't come through their API, but you can get information about like where was the satellite launched from and who manages it and what is its intended purpose. A lot of really cool things. Looking at different satellites because there's a lot out there, and they'll show you the most tracked satellites, the most recently launched satellites, a lot of information. So this is really cool. And they send you something called a TLE, or a two-line element. And what that is a description of the orbit itself. So it's a handful of different parameters. It's relatively complex, but basically what it's defining is how circular is the orbit around the Earth, because your orbit can be very circular or it can be a lot more elliptical. It'll tell you, how far away from the Earth's surface is that orbit, and like how it's rotated in 3D space, essentially. You can take that information and put it into open source software called gpredict. gpredict's really cool. This was relatively new-ish when we did this project. Now it's probably like about 10 years old. It does a lot of really cool things, including showing you the paths of satellites. And this screenshot is from 5 years ago, so it may be slightly different now, but I think it mostly looks the same. You can see the footprints of where you can see the satellite from. This does not tell you like downlink footprints from where you can actually listen to. This just means you can see the sat there. This chart here is a polar chart to show you this center location as if you were to look straight up. And as you look towards the horizon and look perpendicular, you'll go down to the outer ring there. So you can say, hey, here's this NOAA 15 satellite. It'll tell you at what time as it moves across here where it's going to be. So we know that this one, if south was over here, it would be coming up and over in this direction. Really cool. In addition to this, I got to hack in with some other people, some upgrades to their serial output. At the time, they were just adding some like serial output from this program so you could do other things with it. And so we took the serial data out of there, piped it out to a socket so that way I could use it in a Python script to use serial data out to our controller. This was our very first read. It was really, really late, probably like 1 in the morning, and we were able to get a small amount of read off that GOES. So technically, the GOES satellite that we used was GOES 16. That was decommissioned and deorbited, so now it's sitting out in the graveyard orbit and it's no longer functioning. And that used LRIT. This protocol is no longer used by the geostationary weathersats. They replaced that with HRIT and the GOES-R satellites. There are still 3 GOES satellites out in space that are just kind of hanging out as like an emergency backup, but now we're pretty much using just the GOES-R satellites. So this is actually all the detail and information for the modulation scheme and the transmission of that RF signal that they're going to beam back down. Their data is a little more complicated, a lot more unwieldy than the original one. And so I used GOES tools, which is now probably not a good option. I would not recommend using this tool anymore. There's a lot better tools out there, and we'll talk about that at the end. Basically, what this would do is you would define like, hey, I'm connecting with this radio equipment. I'm doing all these things. I'm looking at GOES, and if it can identify everything, you have one tool that will demodulate and decode the stream into packets. You have a separate tool which will take those packets and convert it into files and images. And then you have one last one which will combine a bunch of the files and images into like false color graphics to like merge everything together. So what kind of data do we get out of this stream? It's a lot better and obviously like a lot cooler to look at. These are some stitched together images. There are 32 spectral channels that are analyzed by sensors on the satellite that they will send down, and they send them down in a 5K by 5K orientation. So every single one comes in like 5K by 5K image, and then you can post-process them to merge them into different things. So in this case, we see channel 15 and channel 9, and we just took a short burst of frames and turned them into a GIF. These are how they're doing analysis for most of like your wind streams and like how all like the atmosphere is moving around to analyze for weather. So these, when you look at this, you can see like the entire sphere of Earth in this view, right? And what this equates to is approximately a third of the Earth's surface in view at one point from this set. GO-16 was positioned roughly, I think, like 89 degrees west. It hovered over kind of South America on the equator. That's something I didn't mention earlier. All the geostationary satellites, if you want them to be pretty much in the same spot, they need to be around the equator. Some stations, and I say some stations, NOAA has several stations that do this. They get assigned different slices of the work, and they will receive those same images that I just showed you. They will do analysis. They will apply modeling to them. They will rebroadcast these images, and you can see timestamps on the bottom. They will process them, add their like weather modeling stuff of like where currently is like actual like rain occurring, and they will transmit that image back up, and it will be received down by every local weather station in the US. So this gets kind of pre-processed at a site after they receive the other data, then rebroadcast up to the satellite and bounce back down for everyone to receive. Why NOAA doesn't use the internet in 2020 or today, I have no idea.
Heather goes. I use it a lot.
They do. They've gotten a lot better about sharing, but they still rely on this mechanism for communication. So, like the workflow for meteorologists, all of their data still comes from the sats. I don't have images, and I don't have the files here to show. Every weather station in the U.S., all the meteorological sites, their radomes are to talk with the GOES satellites, and they take all their local metrics, they package them up into literal ASCII text files, send it up to the sat, and everybody else receives that. Every station has their own dedicated time slot, so they can continually send updates of like their temperature, barometric pressure, all the weather data. It's really, really cool to like go in and read all those text files. But again, they use that rather than the internet for a lot of their workflow. You can also combine all of those channels into, we just call them false color images. It has all the spectral data and images to render full color graphics.
I'm just curious, is that a different channel on the same satellite that they just pulled back down by meteorologists?
So the way they do it's all packetized. So everything comes through one comms channel, but what they do is they break out the images per spectral analysis channel. So you get like basically different IDs for the decoded data, and they'll be like timestamped with an ID. So this is a GIF of a handful of different images that we were able to collect and run through all those 32 channels. They do all look like this when you receive them. None of them will have color. They're all entirely monochrome. And through some fancy math and I don't know, some extra information that I didn't program any of that part. We ran a tool that converted them into graphical things that we can see. And this is going to be probably the best selfie that I feel like I've ever gotten of myself. This is just a partially zoomed in. You can actually zoom in on these really far. There's a 5K by 5K graphic, and this is like, I'm still always impressed. It's so cool. When goes, fun fact, who here had an iPhone like when they used to have like the default graphic was the Earth? That was one of the first ever pictures taken from goes. It was actually really cool. And we stayed up really, we got up really early and captured a sunrise. One of these days, I'm just going to stay up for an entire 24 hours or like 18 hours early morning and capture an entire run. A lot of people out there do this. There's an entire group of like WeatherSat monitors who contribute to reads, and some people have online stations where you can just watch the pictures. They have websites that automatically update after they receive the scans from NOAASats or from GOES. So this one is from the USA Satcom WX under someone username of Sandwich Maker. And so there's some pretty cool ones. There's this. Here's a GIF graphic from that same user's upload. And the last thing I have is a couple different other sats that are not Go's and not Noah's. So this is Feng Yun, and this is a Chinese weather sat. These are actually pretty interesting. They have a bunch of other data that they send back down. Not all of their data has been decoded. They'd use APT for like all the video stuff, just like our Leo sats, but they have other data channels that are adjacent in the spectrum. You can find information for decoding these and like the Russian meteor sats pretty easily online. This, speaking of which, this is a METOP. This is one of the meteor satellites from Russia. So if you want to do this, what do you need to know? First off, like the NOAA stuff for like the Leo sats, that is like so well documented, very, very easy to do. But if you want to try and go and hit goes, you have to understand that now some of these satellites and a lot of the information online doesn't match current. So like make sure you're reusing like up-to-date current sources. Recently, they decommissioned Go 16, which is what I used for all the graphics for this. We had a decommissioning party and poured out a bottle of champagne for the satellite. So the frequencies for these, what we used was LRIT. The HRIT actually has better imagery now and a lot of other extra data, but it's a little bit off on the frequency range. If you're looking near like Go's are, you're going to have to look at the other frequency and your bandwidth is going to be a lot different. So you just need to mean like how you're looking at it, the analysis. If you are trying to compare what someone's like screenshot looks like from a tool where you're looking at the frequency spectrum, just make sure that you're paying attention and looking at the right stuff. The MWin is a different downlink service. We didn't decode that. I don't know. I can't remember exactly what's on there. But the satellite also hosts that. I think that's where some of the other additional data comes from, or for the text. So I'm not quite an expert on that. So please don't ask me about MWin, but anything about like the HRT, LRIT, I can help with. I don't know. You can use a much better tool called SatDump. I feel kind of cheated. This is the second time in my life where I used to do things the hard way, and now people have an easy tool, and I feel bad about it because I had to put in a lot of work. The first was having to build really crappy 3D printers 15 years ago, and now I have a Bamboo Lab printer that just does everything. So SatDump's a really cool tool. It supports a lot more radios than the old tools did. A lot of the old tools only worked with like one or two specific radio chips. You can record stuff, you can decode and process the data from a bunch of different satellites, not just the ones that we looked at here. You can do that decoding live, so you can just like see imagery as it comes in. It's really great. And instead of having to do all of those tools and everything separately, building your own tracker, building all these other things, you can just run it all in one tool. And then there's a couple other projects like Open Rotator and like SatNogs that'll help with like the actual tracking mechanism. So you can look up like how to build a new like an antenna tracker, and other people have open source designs that are absolutely phenomenal. If I were to ever set up a new one, I would not do it like we did it. We were just trying to do it for as cheap as possible. So our total price for everything that we spent to build all of our antennas was around $220. In most of that, I would say like the biggest chunk was that like $75 to $80 dish for going to hit goes. But that's all I have. Does anyone have any questions?
I'm just curious. So on the budget end, the one you kind of started with, is the best you can hope for then just kind of like getting a signal, but not really getting anything you can decode?
Yeah, I mean, you can if we actually had like tools and like a decent workshop and weren't trying to solder over a paper plate, you could probably, I mean, a basic like copper conductor dipole antenna can get really good results. You just have to be a lot more careful about like the actual assembly to like reduce any type of interference because of like just having a bad antenna. We did get some like almost lookable images, and we were getting very clean images on the framing, so we weren't sure why. Some of that could be just because of like some poor weather conditions or other things too at the time we were testing, because there's a lot of snowstorms in Pennsylvania where we're at. So, But a lot of people get really good reads with dipole antennas from those satellites. So you could absolutely buy a $20, $30 RTL SDR and a $15 coil of copper wire and make something work. Any other questions?
So for the image creation, is it kind of the same? Are you guys using kind of the same stuff as like astro or like astrophotography with color channels, or are you guys?
So for like goes,
Yeah.
so as part of Go tools, they have a subset. Ghost Proc will help you convert that, and there is I think it's a like a flag in Ghost Proc to set up where once it has all the images, if you have enough, it will then generate the false color images.
So you don't need to worry about packaging.
No, you're not. We didn't manually do any of that. There was already an existing tool that would apply all the math to do so. All right. Well, we'll wrap it up there. If you have any other questions, come find me. I'm more than happy to chat about this or like any other satellite, anything. Thank you for coming.